Now, so we welcome our second speaker, Matej Hoffman. He is associate professor at the Czech Technical University and head of the Humanoid and Cognitive Robotics group. He holds a PhD from the University of Zurich and postdoctoral work he did at the Italian Institute of Technology. Professor Hoffman's research explores the frontiers of humanoid and cognitive developmental robotics. His work addresses how robots can perceive, grasp, and interact with the world more intelligently and intuitively.
Okay, thank you, Claudio. Hello, everybody. So I'm going to talk to you about robots with a sense of touch. So I'm based in Prague, Czechia, and here are some of the robots that I'm going to talk to you about today. So this is the outline. So let's start with large area tactile skins for safe human-robot interaction. So I'm kind of collecting robots with whole body skins, and so you may ask, why is that useful? So I think that the main thing really is human-robot interaction, and this has two aspects to it. So one is safety, contact detection, localization, reaction, and the other is for social interaction. And one perhaps less obvious aspect how you can use whole body skins is for self-calibration. So I'm going to talk to you about that as well. So let's warm up with the safety. So what can skin do for safety? So safety, there's legislation, there are standards like this one on collaborative robots, and there are different regimes prescribed that regulate, how you can safely interact with a robot. This one is called power and force limiting. In that regime, you can actually, a moving robot can actually collide with you, the operator or the human, but the forces have to be within limits. So that's shown here. So there is the evolution, this is the impact, this is the time, and this is the first half a second after contact, which is called transient contact, and the after half a second, it's called clamping, like clamping to the table, or quasi-static contact, and there the limit is only half of the original. And so how do skins play into this? So these robots, they need to recognize that there was contact and they should react appropriately, typically simply stop, okay? And so let's say we get a robot, we put skin on it, so how fast can we then go? So that's the question we asked ourselves. So in this study, we took 3 robots, one big industrial robot, and then 2 collaborative robots, and we put this whole body skin on them. And we ran like 2,000 collision measurements with and without skin, and with the passive skin and the active skin. And we got results like these. So what does it mean? So that's the same kind of evolution after impact. And this would be the KUKA IVA without the skin, this one, the blue one, and this would be with the skin. This would be a UR robot. And you see that, with the skin, active or passive, I cannot go into the details here, you can really get a substantial reduction of the force. And that means if you're substantially below the limit that is allowed, you can actually get faster. So then it boosts productivity. Okay, so that's very simple. I get skin, I detect the collision, I stop. So what if we want to do something more sophisticated? So that's this case study we did on the ICAP humanoid robot. So the ICAP has this whole body skin. Everything that is covered in blue is sensitive skin, so like 4,000 receptors. And so the ICAP here is playing a card game with me. So I'm throwing the dice. And based on what is on the dice, I should pick which card to point to. It's cognitively quite demanding, so I would typically lose. And so in order not to lose, sometimes I cheat. So I basically push the robot away, which was exactly what this scenario was about, right? How do we do this kind of physical interaction and how we get skin into it? So we designed a controller for the upper body of the ICAP that commands these 17 degrees of freedom and takes into account simultaneously these tactile obstacles when I push him anywhere on the body, and also visual obstacles. So you see that the key points on the body get detected. Each of them becomes one obstacle, and all these tens of obstacles are fed into the controller in real time. There is one additional modality. There's a kind of blind spot at the back of the hand of the ICAP, and there we put the proximity sensor. And so this is how the controller works. If you're interested in details, please come to this session tomorrow. But the core is basically here. So it's a quadratic program. We do differential kinematics, and here is the task, which is the reaching task. Point to the right card. And here is a lot of constraints. The most important are these obstacles. So from all the 3 modalities, we have like a unified way of mapping them into the joint space of the joint velocity space. They become constraints that are basically every 10 milliseconds fed into the thing, and then it can, as long as the robot can solve both the task and the constraints, because it's highly redundant, so that's what you were seeing. This last block up here is the ensuring that the motions are smooth and biological like. Okay, self-contained robot calibration through self-contact. So traditional robot calibration procedures would be open loop or closed loop. In both cases, they require some kind of external setup, like a laser tracker or some kind of constraints that, for example, fixate your end effector to the table. So that's not practical. Current robots, they are often cheap and from elastic materials, so they may require frequent recalibration. But at the same time, they come with a set of affordable and increasingly accurate sensors like cameras and tactile and force sensors. So that creates at the same time an opportunity. So together, this paves the way to closing the loop within the robot itself. So we took a industrial dual-arm robot, and we did first implement these traditional approaches like open-loop calibration with an absolute tracker and closed-loop calibration with contact with the plane. And then we did this self-contained robot calibration. So in two ways. One is self-contact, so how does it work? So imagine that you close your eyes and then basically contact your index fingers like that. And now do your forward kinematics for your left arm, you get some XYZ. Do it for the right arm, you get some XYZ. Maybe it's not going to be exactly the same. So that gives you an error term that you can use to calibrate your body model. What is self-observation? So take just one finger and then close your eyes. Now imagine where on your left retina it's going to be. Then open your left eye. Maybe it's going to be slightly shifted. Gives you another error signal. And so this you can put into equations. You can solve it with nonlinear least squares optimization. And so what did we learn by comparing these methods? First, we learned that self-touch is really robust and effective, and it's better than the methods relying on cameras because they don't see the depth typically. And we also learned that there is a synergy. So if you use multiple of these methods at the same time, say self-touch and self-observation, you can actually get much better results, and also you can see it in the observability of the estimated parameters. And so this slide is like an overview. We did it in different robots. It started with the ICAP doing this self-touch, and because it has this spatially calibrated skin, you can use it to improve the kinematic model of the robot. Then we added the self-observation. On the bottom right is the industrial robot. We made a kind of big humanoid out of it to prove that. And the bottom left part is a now robot that got it was retrofitted with skin, so it was not spatially calibrated. And there we used the self-touch and forward kinematics to actually calibrate where the individual tactile sensors are. Okay, next topic is baby humanoid with tactile feedback. So, so we've got this, this baby humanoid. Let's say in this case it's a 4-year-old. And so we would like to have a biomimetic representation of its skin surface. In humans, we have this somatosensory homunculus, right? That probably many of you know. So this is this distorted map of the skin surface. So we wanted to get something like that for the ICAP. And actually, here you already see the final product. So this is this cortical sheet of the ICAP where you relay the activations on its skin surface. What you see on the left is how it was trained. So I was going around the ICAP with my thumb for about half an hour. And because my thumb is bigger than any single taxel, from these co-activations, it actually learned to develop this map. This, however, is just one building block, one little piece of the puzzle. What we are actually after is really understanding this infant sensory motor development in the first year. Like, how do I do it to reach for an object, or how do I reach for a stimulus on my body, which is what the baby is doing there right now. So we put a stimulus and it needs to find it on the body. And so we have the ICAP as a model of that. So we follow this understanding by building methodology that the robot is an embodied computational model of child and brain development. And the important part is that we can instantiate these complete sensory motor loops with motor, proprioception, touch, and vision. Okay, the last bit, which is kind of the most haptics bit, is we took two sets of objects the one here is very difficult. It's samples from a manufacturer of matrices. And we took 4 different robot hands or grippers, and also with different action parameters. And we did this single grasp data collection. And we wanted to see what are the relative importance of these factors, like which hand, which sensors, which actions for the object discrimination. So the input was basically the stress-strain curves from the individual grasping devices. And so we tried with and without features. We tried different classifiers, and we also did an unsupervised analysis to understand the feature space. And so here is the classification results. So this is for the individual hands. This is for the 2 object sets, and this would be one column here would be trained for an individual action parameter, like one gripper configuration. The rows would be then the classifiers. So what did we learn? So the sensor pre-processing features, no features, doesn't seem to matter too much. The classifier also doesn't seem to play such an important role. The action parameters do matter. So for example, whether you grasp it with the thumb opposing or not is important, and even the speed is important. So for the 2-finger grippers, slower speeds, even though we controlled for the number of samples, actually yielded better discrimination. And yeah, the most the powerful tool is which gripper you choose. And so why is it that particular grippers do it better? I'll refer you to the article. We did some ablation studies and some study on generalization across parameters. But I also want to show you the unsupervised analysis. So if you lump all the features you collected across the grippers together, so here you see the colors are the different objects from the 2 sets. So this is principal component analysis, the first 2 principal components, and as you would expect, by far largest source of variability is the grippers itself, right? So for both sets, on the right, this is actually, both of them are 2-finger grippers, but still, this is a really large source of variability. So yeah, cross-embodiment haptic classification seems to be challenging. Now, each square now is just a single gripper. But the clusters here, again, are not the objects, but are actually the action parameters, the grasping configuration or the speed. And, for some speeds, for example, separate better the object. So grasping action parameters are a key source of variability, and data from different grasping configurations, and even speeds should actually not be mixed, is what we learn here. Okay. Foundation models for haptics. So yesterday there was this, elephant in the room discussed. So my take on this is the following. I did my PhD in the Rolf Pfeiffer's lab in Zurich. So I really believe that, human cognition is embodied and that perception is active. And behavior is a result of this brain-body environment interactions, right? So you have loops, between the body and the environment. So the brain is only, one part of this whole puzzle. And this embodied AI and foundation models, so we just put up on arXiv a kind of opinion piece. So I argue that this is weakly embodied, that basically it's kind of, this is only doing this outer loop and typically at a very low frequency. So it's a kind of sense, think, act architecture. And it's learning from data sets which are passive, and hence it's intrinsically limited what you can learn from them. And also for cross-embodiment learning, so biology, found different brains for different animals for maybe for good reasons. So this is a question, whether we can actually do that. So case in point, haptics. Haptics is fundamentally active, and the hand embodiment, as we just saw, is extremely important. Number of fingers, placement of sensors. So yeah, foundation models for haptics seems challenging. I want to invite you to this conference we're organizing in Prague on development and learning. There is still one late-breaking results is open. Talk to me. I have flyers. Find me. And with this, thank you for your attention.
Thank you very much. We have time for one very quick question, please.
Hi, thank you for the wonderful speech. So ever since the iCub robot, we haven't really seen a lot of whole body tactile sensors applied to robots. Yeah, proprioception is still widely actively used. Can you speak a little bit more on how the whole body sense of touch plays in the role of somatosensation?
All right. Okay, so somatosensation, so for us humans, it's touch and proprioception. It's kind of linked together, right? So for robots, proprioception is, let's say, joint angles. And so this is very different from humans because joint angles, the joint encoders are very accurate, very fast. It really gives you the state of the joint, which is something that we as humans probably don't have. We're not very good at that, right? So for us, we have to integrate several signals, and also we're much more sensitive to changes than states. So I think actually this homunculus I showed for the touch, that was relatively straightforward how to do that. We have also been working on how to do a homunculus for proprioception. That's much harder because it's not even clear what the brain runs on. Is it like forces, or is it joint states, or is it just changes of joint states? So there I think is a big gap between humans and robots, and we still have to solve that.
Thank you.
Let's thank again our speaker.